Line integral. The integral expression for the work done in moving a point charge group from one position to another, which in vector analysis notation always takes the form of the integral along some prescribed path of the dot product of the vector field and a differential vector path length dl. Without using vector analysis, we should have to write W is equal to negative q integral of E sub L dl from initial to final, where E sub L is a component of E along dl. A line integral is like many other integrals which appear in advanced analysis, including the surface integral appearing in Gauss' law, in that it is essentially descriptive. We like to look at it much more than we like to work it out. It tells us to choose a path, break it up into a large number of very small segments, multiply the component of the field along each segment by the length of the segment, and then add the results for all the segments. This is summation, of course, and the integral is obtained exactly only when the number of segments become infinite. From this equation, the path is divided into 6 segments: delta L sub 1, delta L sub 2, up to delta L sub 6, and the components of E along each segment denoted by E sub L1, E sub L2, up to E sub L6 are using vector equation. W is equal to negative q times the quantity E sub 1 dot delta L sub 1 plus E sub 2 dot delta L sub 2 up to E sub 6 dot L delta L sub 6. And since we have assumed a uniform field, E sub 1 is equal to E sub 2 up to E sub 6. W is equal to negative QE dot delta L sub 1 plus delta L sub 2 plus up to delta L sub 6. What is the sum of vector segments in this parenthesis? Vectors add by the parallelogram law, and the sum is just a vector directed from the initial point B to the final point A, L sub BA. Therefore, W is equal to negative QE dot LBA. From this figure, it is a graphical interpretation of a line integral in a uniform field. The line integral of E between points B and A is independent of the path selected, even in a non-uniform field. This result is not in general true for time-varying fields. The final position is given the designation A to correspond with the convention for potential difference, as discussed in the following section. Remembering the summation interpretation of the line integral, this result for the uniform field can be obtained rapidly now from the integral expression. W is equal to negative q integral of E dot dl from B to A. As applied to a uniform field, W is equal to negative QE dot integral of dl from B to A, where the last integral becomes L sub BA, and W is equal to negative QE dot L sub BA. For this special case of a uniform electric field intensity, we should note that the work involved in moving the charge depends only on Q, E, and L sub BA, a vector drawn from the initial to the final point of the path chosen. It does not depend on the particular path we have selected along which to carry the charge. We may proceed from B to A on a straight line or via the old Chisholm trail. The answer is same.